Hi, and welcome to our second podcast on medical statistics. Last time we looked at formulating a clinical question, and then this week we're going to look at descriptive statistics and standard scores. In more detail, what we're looking at this week is two particular types of descriptive statistics, that is, measures of central tendency and measures of spread. And then we'll also look at standard scores and the normal distribution as well. Now, this podcast might not set your world on fire, but again, it's important fundamental stuff that we really need to understand before we move on to our next topic, which will be hypothesis testing. So if we're talking about descriptive statistics, then it's important that we define what they are. One reason for calculating statistics is so that we can describe our data, answering questions like how many of our population fulfill this criteria, or how large is this measurement that we've taken from our population, or how spread out is our population, or how skewed is this data set. So asking questions which describe the data. Another use of statistics is to test hypotheses, or to make inferences from our data, from our sample to the whole population. So that's answering questions like, is the mean of our population greater than such and such? The first of these two types of statistics then is called descriptive statistics, whereas the second is inferential statistics. And it's the first of these that we're really going to consider briefly today. In particular, we're going to talk about measures of central tendency and then measures of spread. So measures of central tendency are often referred to as averages. Now, before you click on stop or close your browser window because you can't believe that I'm about to talk to you about averages, then bear with me for a moment and think about this example. Suppose that you've decided you want to study what happens to the arterial pH of patients after some major operation that your team does. So you sample 100 post-operative patients, you take some arterial blood and work out the pH. And what you want to do is figure out what the average pH is for these patients. Which average would you use? And have a think about it for a moment. Now, if you decided that the mode was the best average to use, then you might want to go away and do a bit more reading about averages before you come back here, because that's really a bad choice. If you went for the median or the mean, then that's better, and those would potentially not be unreasonable choices to use. If you thought, because pH is a log quantity, then I'd like to take anti-logs and then take the mean of the hydrogen ion concentrations and then take the log of this again, then well done, and you can skip to the end of this podcast. Now, I say that not to make me sound clever or to make you sound less clever, but just hopefully to make you realise that finding averages is not just as simple as working at the mean of the data that you have. Well, sometimes it is, but it's not necessarily. So I'm not going to spend any time defining averages, you should know that already, but I want to spend a bit of time thinking about which is the best one to use. Now, we tend to think that the mean is the best because when we work it out, it's got loads of decimal places, and so that makes it look really accurate, whereas the others tend to be whole numbers or just categories. But I want to try and persuade you that that's not necessarily the case. So there are some times when really only the mode will do. Consider a study that looks at the hair colour of patients presenting with malignant melanoma or Dupuytren's contracture, whatever you like. There's no way to even calculate the mean or the median of somebody's hair colour, and so certainly in cases where you have categorical data, the only average really available to you is the mode. Likewise, there are some times when it makes sense to use the median. If you think about, say you had a bunch of patients who had bladder cancer, and you recorded the stage of their cancer. So some of them would have PTA, some of them would have PT1, PT2, PT3. Now, you could use a mode to look at the average of these patients, but then again, because we know kind of an order or a ranking for these stages, you could also work out the median. But it doesn't make sense to use the mean because you can't divide PTA plus PT1 by 2. And another example could be length of stay in hospital. So say you're looking at how long your patients stay in hospital after they've had their operation. Now typically we only record this data as length of whole days. So we say somebody has stayed 3 days post-op, but we wouldn't record it to the kind of accuracy where we said somebody stayed 4 days, 12 hours and 13 minutes post-op. That's just not what we do. But it's not uncommon to see reported mean lengths of stay. But does that really make sense? Suppose that you had somebody who had stayed 1 day and 23 hours after their operation. Well, we would record them of having a length of stay of 1 day because we record in whole days. And suppose you had a second person who had stayed 2 days and 1 hour after their operation, then they'd be recorded as having a length of stay of 2 days. So you'd have one person who stayed 1 day, one person who stayed 2 days. If you look at the mean of those two patients, then you would say that the average length of stay for these patients is 1.5 days. And what does that even mean? Does that mean that on average people were discharged at 12 noon the day after their operation? Or does that mean that they stayed for 36 hours from the time they left the operating suite? It doesn't really make sense. Whereas if we worked out a median, then typically we would get a whole number answer. So we'd say that the median length of stay was 1 day or 2 days. And that makes sense because that's in the same units that we're measuring. So clearly the type of data that we have can guide us as to which measure of central tendency or average we use. But it's still important to look at our data to make sure that the statistics that we're using make sense. So here, for example, is a nice symmetrically distributed set of data. And it would seem reasonable that we could use the mode, the median or the mean to describe the central tendency of this data depending on what type of data it was. If we look at this next example though, so this data is now skewed to the left, and you can see that the mean and the median don't estimate where intuitively we see the average value to be particularly well, so they both sit off to the right. So it might be that either we say that the mean and the median are not good measures to use here, or it might be that if we came across this situation then we would need to think about transforming our data. And then here's another example whereby if we just blindly went ahead and asked a computer to calculate a mean or a median, then we would have missed something. In this case the data is bimodal, and it should prompt us to think about whether we need to split our sample into subgroups. And you'll see that if you were to go ahead and try to work out the mean or the median for this data, then the number that came out would be exactly the number that you didn't want. It'd be one of the least common values. So I hope what we've covered is that in order to pick a good measure of central tendency, you need to think about what type of data you have, but then also you need to have a look at your data and see whether what you're doing is appropriate. So the next descriptive statistic I wanted to talk about were measures of spread. And here we're talking about things like ranges, quartiles, and measures of variation. They don't really make sense in categorical data. So really here we're talking about discrete or continuous data. And so the thing about our data that we're describing here is how spread out it is. So if you look at the example above, we've got two nice symmetrical distributions. They both have the same mode, median and mean, but the red distribution you can see there is more tightly spread around the mean, whereas the purple one is more spread out. And then the question is, what statistic can we use to quantify this measure of spread? And to help us think about that, I want to look at two distributions here. Now, it's a bit contrived, but suppose you do one experiment and you have 6 results, and 3 of the results come out as -1, 3 of the results come out as +1, and then hopefully you'd agree with me that a good number to represent the spread of this data would be 1, because everything is 1 away from the mean. And suppose you do a second experiment where, again, you get 6 data points. 3 of them are -2, 3 of them are +2. Here you would expect whatever number you come up to represent spread to be 2, because everything is 2 away from the mean. And so there are a number of different ways that you could try and measure spread. So for instance, you could just find the difference from each of your data points from the mean and add them together. And you could call this the summed deviation. Now the problem is that in both of our data sets here, when you added those together, they would come to 0, because all of the minus ones, those which are 1 below the mean, would cancel out with the positive ones, those which are 1 above the mean. And in the second data set, the negative 2's, because they're -2 from the mean, would cancel with the positive 2's, which are 2 from the mean. So that would be a relatively useless way to try and calculate spread. The second thing we could do would be to just look at the size of the difference from the mean and average this out. So in the case of our first experiment up top, each of the -1's is a distance of 1 from the mean, and the positive ones are a distance of 1 from the mean. So the average distance we'd get here would be 1. That's reasonable. And then again in the bottom, each of our data points are a distance of 2 from the mean, and so the average here we would get would be 2. And this measure of spread is called the absolute deviation. It's not used very much because there's another measure of spread which turns out to be more convenient in terms of the way that calculating statistics works. And so it's probably the one you've heard of most, which is called the standard deviation. And in this, we take the difference of each data value from the mean, we square it, which makes everything positive, we add it together, average it, and then take the square root. And if you worked out the standard deviation for our first set of data here, that would be 1, and the second set of data would be 2. So in our cases, we're getting the same answers as the absolute deviation, but that's not always the case. So we've talked about absolute deviation and standard deviations, and there are other measures of spread. So you've probably heard of interquartile range, and then you could use the range. So next I want to go on to talk about standard scores. And these turn out to be relatively important when we come on to later topics like hypothesis testing. So imagine that you're revising for an exam, say you're revising for your MRCS, membership of the Royal College of Surgeons. You work hard and you pass and you get a score of 72%. Great. The downside to this is that you have a friend who passed his MRCS the year before and he had a score of 75%. Now, competitive as we all are, what we'd really like to know is who did best. Now, your friend naturally says that he did better because he scored 3% higher than you. But your argument would be that clearly the exam was much harder the year that you took it. And so, in fact, you did better. And standard scores is one way of answering this argument. And clearly it depends on who took the harder exam and where they came. So let's look at an example. Suppose that these are the distributions of the results of the exam. In green is the exam that you took, and in red is the exam that your mate took. So you can see here that whilst your score was lower than your mate's, clearly you've done a lot better because you were really near the top of the distribution of scores for the MRCS the year you took it, whereas your mate is somewhere below average. So you could say in this case that whilst you got a lower score, you probably did better. If we look, however, at this graph instead, so same idea, the distribution of your MRCS is in green and of your mates is in red. Suddenly it's a little bit more difficult to tell what's happening here just by looking. I mean, the scores are quite close, but who's done better here? So what we need is a bit more of a robust way of deciding how we compare between two distributions. And one way to do this, and the idea which lies behind standardised scores, is to ask the question, how many standard deviations above or below the mean does the score lie? And this is useful not just in comparing scores like we have here, but it's foundational in some kinds of statistical tests, like the student's t-test, for instance. So if your score was 1 standard deviation above the mean, then you'd be said to have a standardised score of 1. And if somebody else had a score which was 1.3 standard deviations below the mean, their standardised score would be -1. And the good thing about standardised scores is that you can compare them across different distributions. So in our example, different exam sittings, you could still compare two candidates' standardised scores. Okay, so the last thing I want to come on to talk about today is the normal distribution. It's an important distribution because it crops up loads in nature when we measure weights or heights, when we look at test scores. And another reason it crops up a lot is due to a relatively central theorem in statistics called the central limit theorem. That's not something we're going to go into detail in now, but if you wanted to put a quick search on Google, would point you in the right direction. So we know a lot about the normal distribution. Just by looking at it, we can see that it's a symmetrical distribution. But more than that, we know what proportion of the data lies within, say, 1, 2, 3 or 4 standard deviations of the mean. So the diagram above, on the x-axis, the label is numbers of standard deviations above or below the mean, and then written within the diagram itself is percentage of the data. So that shows that about 68% of the data lies within 1 standard deviation of the mean, 95% lies within 2, and 99.7% within 3. And likewise, if we know that a population is distributed normally, then you could ask questions like, what's the probability of selecting an individual from it that is further than 2 standard deviations from the mean? And if you look at the diagram above, I think you'll be able to persuade yourself that there's about a 5% probability of that. Think about the situation where we measure the serum sodium levels of healthy individuals. Then this would turn out to be distributed normally with a mean of about 140 millimoles per litre. Suppose a patient is admitted and you measure their sodium and you find that it's 155 millimoles per litre. Then you could ask the question, do I think that this patient comes from the population of healthy patients? Or given that I know that this level of sodium is normally distributed, do I think that this patient is too many standard deviations above the mean to have come from this population? That is to say that this is a pathological sodium level. And typically, when we look at lab results, the reference ranges we get are plus or minus 2 standard deviations from the mean, or those values with standardised score +2 or -2. And when we look at hypothesis testing, we'll see that we use a very similar logic. Is the result that we're presented with one that makes us want to reject the null hypothesis? So we've talked about descriptive statistics, we've defined what they are and how they differ from inferential statistics. We've talked about measures of central tendency, averages, some pitfalls in using them, and sometimes when they're useful and when different types are useful. We've talked about the rationale behind measures of spread, some different types of measures of spread, and then also we've talked about the normal distribution, and we've started to touch on some ideas which will be important when we come to think about significance and hypothesis testing. These first 2 podcasts have really introduced some foundational ideas about how we ask clinical questions, and then some of the bread and butter of the types of measures and distributions that we come across. Next time we'll be talking about hypothesis testing.